If my memory serves me right, last meeting we have discussed the intro to distillation and have covered the methods under type 1. So type 1 distillation is distillation where there is no reflux. So the liquid is condensed and then separated from the vapor in those types of distillation. So for this afternoon, we will continue with under method 2, wherein there is already reflux, a part of the condensed vapor leaving the condenser, and the top of the column is being returned back into the column so as to improve the purity of the final product, which is the distillate. So we are now on the types under method 2. So in your handbook, you can refer to section 13-5, specifically on figure 13-2. So you have the different types of distillation there under distillation with reflux. Now, to add to fractionation or rectification, distillation with reflux, we have also extractive distillation under method 2. So in here, we are employing the difference in the volatility of the two components to be separated. So this is used when the difference of the volatilities of the two components that are to be separated is very small. We have discussed this meeting that the greater the difference in the concentration of the volatile and the non-volatile components, the easier it is to separate the components. But in the case of extractive distillation, when the volatilities of the components that we need to separate are very near each other, meaning their difference is so small, then we can use extractive distillation. In here, we're using what we call a mass separating agent, or an MSA, that will increase the volatility difference. That way, we will have easy separation for the components. If not, then the usual process of distillation will really be very, shall I say, producing a lengthy process of separating the components. If not, it would also be near impossible to separate components. Now also, under this method, we have azeotropic distillation. So it's an alternative for extractive distillation. This time, this is applied to azeotropic mixtures. Now, mixtures that are said to have the same composition when they reach a certain temperature. As such, it's difficult again for them to be separated. If that is the case, then an addition of an MSA will be an alternative, or we can use azeotropic distillation. Okay, so this is under method 2. A more general process flow for the fractionating tower, or schematic for the fractionating tower, is the one that we are seeing here. This is taken from, if I'm not mistaken, from McKay. Okay, this is our steel. This is how we represent our steel. But when you represent your figures later on, when you submit your solution, you need not present it like this. It could be a simple rectangular box, and that would do. Okay, so in this steel, you have the reboiler at the bottom. So this could be presented as a very simple circle. Now in the reboiler, you have the steam supplied. So the purpose of the reboiler, as we view, is to convert part of the liquid that has been collected at the bottom of the tower to have it converted into vapor. That will flow countercurrent to the liquid that is going down. The rest that was not converted into vapor is withdrawn as the bottom's liquid. Okay, so that's the purpose of the reboiler, to produce the vapor that will flow countercurrent to the collected liquid at the bottom. Now, in here at the top of the column, you have the vapor being introduced into the condenser. Of course, the primary purpose is to condense it into liquid. Part of it is being returned into the column as reflux. So that's your reflux liquid. And the final product, the desired product, is that distillate. It's also in liquid form. So the concentration of the vapor that goes up your column, the concentration of the distillate, and the concentration of reflux are all equal. So they are only in different phases or state, but the concentration is the same. So your feed, this is your feed. In this particular simple schematic diagram, you have only a steel that has a single feed. But in the industry, there could be several feed, or we call it side feeds, in the same way that there could also be several withdrawal ports in here, depending on the type or the fraction of the, let's say, for example, of petroleum or crude oil that needs to be withdrawn at that particular section of your column. So there could be several withdrawing ports in here, or streams as well. Okay, so this is the very simple representation of a fractionating column or a distilling column. I'm using the term fractionating column or rectification column because we have already this reflux liquid. If we just simply say distilling column or simply distilling equipment, it could be a distilling equipment that does not have reflux return back into the column. But when we speak fractionating column and rectification column, it's automatic that it has reflux liquid. Now, last thing I mentioned about Ponchon-Savaret method. So this is the method that uses the enthalpy composition diagram aside from the standard equilibrium diagram that we are using, wherein we are only required to use material balance. So may it be in the form of an overall material balance or component balance. So in the case of Ponchon-Savaret, we add to that, to the material balance equations, the enthalpy balance or the energy balance, which relies on or uses the enthalpy composition diagram. Now, the approach in here uses the energy balance in addition to the mole balances and the phase equilibrium relationships. Now, the constant molal overflow, which is a primary assumption in the McCabe-Thiele method, is not being assumed in here. So we don't assume constant molal overflow in this particular method if we're going to use it. We're not going to use this method in all our computation because, as mentioned last meeting, it's a trial and error procedure and it's very lengthy. But of the two, the Ponchon-Savaret method is more accurate than the McCabe-Thiele method. Now you can refer to this more info on the concept of Ponchon-Savaret method in section 13, the 16 to 17 of your handbook. Okay. Now, there is this mention about constant molal overflow. So, what is constant molal overflow assumption, which is the main assumption that is being used in McCabe-Thiele method. And this method we will be using all throughout our discussion here for distillation. Now, constant molal overflow assumes that the liquid and the vapor entering a particular plate or stage is the same liquid and vapor that leave that particular stage. Okay, that's the assumption of constant molar overflow. What this means is whatever is the amount of liquid phase or vapor phase that entered or that was processed by a particular stage or tray, that same amount leaves your tray or your stage. If we're going to think of it, you need not be a chemical engineering student to understand. It would be near impossible for a constant molal overflow in a particular stage or tray because there is already transfer of component from one phase to another. But in this case, we assume that that particular transfer as we go from tray to tray is very negligible, or the difference then in the amounts of the liquid phases and the vapor phases that enters and leaves a particular stage is so negligible, the difference in the amounts, that we assume constant molal overflow. Though it's not actually constant. There is always some change, or there is always difference in the amount of the liquid phases that leaves a particular tray. Of course, it follows the same thing with the vapor phases. May difference in sa ila because of the transfer. But in the case of McCabe-Thiele, we assume that that's negligible and that we have constant molal overflow. In Ponchon-Savaret, we don't assume that one. Now, what is the McCabe-Thiele method? So this is based upon representation of the material balance equations as operating lines on the y-x diagram. So in the y-x diagram, that's the equilibrium diagram that I'll be showing to you in the next 2 slides. I've shown it to you last meeting. We will be producing the curve, so that x and y relationship, the mole fraction of, let's say, benzene in the liquid phase, plotted against the mole fraction of benzene in the gas phase, that's your y. So if you're going to plot that, that will produce a curve. So that curve, that equilibrium diagram, or that the equilibrium curve, is the y-x diagram that is being referred in here. In the initial part of our discussion, I will not discuss any problem for now because I want to finish everything, all the theories and concepts behind. That way, when I go to the actual application of those concepts and theories, you already know what I'm talking about, especially when we go to the graphical approach, then we proceed to the analytical approach. This X and Y diagram, especially with the systems that we're going to deal with, in our case, will be limited only to benzene and toluene. Why am I saying that we will only limit our discussion to benzene and toluene? Otherwise, the problem will give you this relationship between X and Y. Because our reference books only give you the equilibrium diagram for benzene-toluene system. We don't have other equilibrium diagrams for other systems. So the main system that is used in the examples and even in the problem is benzene and toluene. If you're going to resort to graphical approach in solving a problem in distillation, it is important that you have this X and Y table or this X and Y data. That way, if it's not benzene and toluene that is given to you, you can plot it. But if it's benzene and toluene, there's no need for you to plot because, as I've said, it is already provided in your books, in our general reference books, both Jan Kuplis and McCabe. So having said that, your assignment for our meeting tomorrow, I will use 1 hour of your dry lab schedule, or 1 hour and a half of your dry lab schedule tomorrow to discuss this one. Please prepare or have ready your X and Y diagram for benzene and toluene. That way, as I illustrate to you how you're going to do the graphical approach, initially, because we will focus on the analytical approach, you will have a table to use beside you. So prepare that for tomorrow. Now, when you use the graphical approach, you need to construct the operating lines. We have 3, specifically, we only have 2 operating lines. The enriching section operating line and the stripping section operating line. However, when you're going to use already the graphical approach, there is this 3rd line that you're going to plot together with these 2 operating lines. And that's the feed line, or we call it the Q line. So the operating lines with the assumption of constant molal overflow class is straight. Without the assumption of constant molal overflow, this particular operating lines, referring to both the enriching section and the stripping section operating lines, will not be straight. So this method of McCabe's TL assumes it that way the lines or the graphs that you will be producing will be straight, the lines that is. So the liquid phase flow rate is assumed to be constant from tray to tray in each section of the column between addition, that's of the feed, and withdrawal of the product points, which makes the vapor rate to be constant as well. So I have mentioned this already. You can read more on this in section 13-18 of your handbook. And this is your column wherein the sections that I have mentioned a while ago is already illustrated. The enriching section is the section above the feed line, and the stripping section is the section below your feed line. If you would be asked where is the feed line or the feed plate located, it is located in the stripping section. Though in all schematic diagrams, it's the feed line actually that separates the enriching section and the stripping section. When we do our overall material balance for distillation class, the feed is equated to the distillate, which is the capital letter D, and the bottom's liquid. So the sum of these two should be equal to the feed. When we do overall component balance, let's say the more volatile component of the two in our two-component system, then we just base it on the overall material balance, and all these phases or streams we just multiply to the mole fraction, of A in each of these streams. So this is mole fraction of A in the feed, mole fraction of A in the distillate, and mole fraction of A in the bottom's liquid. This we set up initially, so we always start our calculations to analytically using this material balance equations. Now, we go to the enriching section. The enriching section of your column, as I have mentioned a while ago, is that part of the column above the feed. Okay? And included in the enriching section is the auxiliary equipment, which is the condenser, which is part of your enriching section, because without it, we cannot have the reflux liquid that is returned in this section to increase the purity of the product. And you have here the distillate. If this is our equilibrium diagram, let's say for example for benzene and toluene, this is the curve that gives you in, let's say, in a picture manner, the relationship between X and Y. The enriching section operating line is this line. Okay? It's the first thing that is being drawn in here, the enriching section operating line. How do we draw the enriching section operating line? You need the mole fraction of the distillate. Oftentimes, it's stated in the problem. If it's not stated in the problem, then you have to determine it using the material balance equation or the component balance equation, or both. Whatever equation you will need, as long as you find the X sub t. That's where your line is going to start, and you are going to have the slope of this line, the slope of this enriching section operating line, computed or calculated based on the amount ln divided by v sub n plus 1. Now, what is this ln and v sub n plus 1? This ln, if you're going to cut your steel in the upper section, is the liquid phase that leaves the nth plate of this section. That's your ln. And the v sub n plus 1 is this particular, you see this particular arrow, this is the vapor phase that enters plate n of this particular section. Now, having said that, of course, you will wonder, how will the problem give us specifically the liquid that leaves the nth stage of the enriching section and the vapor that enters the nth stage of this section? Of course, it's impossible. No problem gives you this. So there's an alternative, another way of finding the slope of this line. Okay, that will be requiring now the reflux ratio, which I'll be discussing in the next slide. Now, you may be wondering why need the slope of this line? In the first place, if you are to draw a line, you need two characteristics of that line based on your analytic geometry. It's either you have 2 points, that way you can correctly draw your line, or you have a point and a slope of that line, or a point and a y-intercept of that line. But it is certain that you need two informations about that line. So in this case, the two information that we'll be using is the X sub t. So you have to project the value of the mole fraction of the distillate from the horizontal axis up until you reach the 45-degree line. This 45-degree line is already pre-drawn in all equilibrium diagrams. If not, if you will be the one to construct this curve out of the pair values of X and Y, then you just draw the 45-degree line on this particular curve that you have plotted. Okay, you draw that particular line and then you project on that line the X sub t. Then, together with that x sub d projected on this particular x and y line or 45-degree line, you either use the slope or the y-intercept of the enriching section operating line. Okay, this is in section 13-18 of your handbook. Now, I mentioned a while ago, it's quite impossible. I haven't encountered a problem that will give you this ratio. So what's the alternative? So that brings about the concept of the, I'll go back to this equation later, class, that gives us to the concept of the reflux ratio. Oftentimes, our reflux ratio, class, is the external reflux ratio. The one that you have here in the slope is the internal reflux ratio. If the problem gives you just simply states reflux ratio, actually it's the external reflux ratio, and it's okay. We use the external reflux ratio in lieu of the internal reflux ratio, because in the first place we already assume that our line is to be straight because of constant molal overflow. So if it's not straight, then these two will not be the same, the external and the internal reflux ratio. But because of the assumption that we have a straight line and that we have constant molal overflow, so the value the problem gives you on the reflux ratio, actually the problem does not specify whether external or internal reflux ratio ina siya. But you are to assume that it's the external or the internal reflux ratio. So in that case, you will use it. Now, going back to the operating line, in any line, you have the y equated to the slope times the x of that line plus the y-intercept. I like to make this bigger. You already have this idea of the xd. So you have already plotted the xd on the 45-degree line. So you need another information that way your enriching section operating line could be plotted properly. What is that information? So you have the choice. You either use the slope of the line. So the slope uses the reflux ratio. Where do we get this, Miss Ali? You get this from the problem itself. Most problem, 100% of the time, the problem gives you the reflux ratio. So from the reflux ratio of the problem, you solve for the slope of the line. Or another option is the y-intercept. So this is the B. So actually, this is your equation comparable to the line equation y equal to mx plus b. So I have noticed in the computation of my students then that they'd rather use the y-intercept rather than the slope. So if you will use the y-intercept class of the line, you will be needing the mole fraction of the distillate and the reflux ratio. So you will use the two. Whereas if you use the slope, you only need the reflux ratio because you solve it based on the reflux ratio. This is the formula for the M of your enriching section operating line. And this is the formula for the y-intercept of the enriching section operating line. Why determine these two together with this? That would help you determine your or properly plot your enriching section operating line. If you have the XD already, for example, just to give you an idea, anyway, we'll have a specific example next meeting. You already placed here the XD. You already projected it on your 45-degree line. Your y-intercept, if you have computed it already, will be in here. For example, it's in here. You may wonder why place the y-intercept here, Miss Ali? Okay, based on the definition of the y-intercept, it's that point on the vertical axis where your line is going to cross. Okay, that's our definition of the y-intercept. So meaning, if you connect this point that you have projected here in the 45-degree line to the vertical axis in here, without you having to draw the entire line. You only draw a line that will not cross, by the way, our curve. You will be able to produce a line. So connecting the XD point on the 45-degree line to the vertical axis where you place your y-intercept value as computed will make this line here. Another alternative is the slope. Now, the extra challenge of the slope, because it would be quite lengthy in procedure, is that you will look for a value of x and solve for y. That way, you will have the slope that you need. For example, you have the slope of the line. We know slope is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. In this pair of coordinates, you already have the xd as 1 point. So it could be this one, the x1 and y1, or it could be x2 and y2. What you need is you assume either the x or the y in here. Using the slope that you have, you'll be able to solve the other. What do we mean by that? Assume a value for x and solve for y because you already have the slope. So now you have the value of x and y, and you plot that particular point in there and connect this one. So that will make this line also. Okay? Now this xd, since it's on the 45-degree line, by the way, will have equal values of x and y because it's right on the 45-degree line. Okay, so your x and y, its slope is said to be 1. So whatever is the value of the x would be the same value for the y. So this is how we construct the enriching section operating line. After that, you will construct the next two lines, which is the steeping section and the peak line. But before I proceed, do you have any questions so far as to what I have discussed in here regarding the plotting of the enriching section operating line? We label this as EOL. Then we still have the advantage of face-to-face classes. So this is our enriching section operating line. This enriching section operating line class is given by this equation. But before I show to you that equation which we skip, because I need to go to the reflux rate, the equation which is the reflux ratio, do you follow my discussion here on how you're supposed to plot the y-intercept and how you're supposed to use the slope? That way you can properly draw your enriching section operating line. Okay, so there's none. So as I've mentioned, this line will have an equation, this enriching section operating line. That equation is given by this equation. We have the material balance equation in this part of the column, this section. So you have a single stream that is entering this section in the broken line box, and you have two streams leaving. That's the reason why you see this B sub n plus 1 is equal to Ln plus D. You have Ln and D leaving the section, and you have Vn plus 1 entering the section. If you do component balance, on this total material balance done only on this section, you produce the equation for the enriching section operating line. This is it. So what you do, you just multiply these streams by their corresponding mole fractions. So for the vapor phase, you use the y. For the liquid phases, you use the x. If you isolate the y subscript n plus 1 on the left side and divide the entire equation by b sub n plus 1, this is the equation that I have jumped to a while ago. Okay, this is this equation that you have seen a while ago. This is the internal reflux ratio. Now it's comparable to R over R plus 1 because as mentioned, the problem does not give you specifically this one. And this is the y-intercept as a function of the mole fraction of the distillate and the external reflux ratio. Okay? That is for the enriching section operating line. Now, what about the stripping section operating line? The stripping section operating line is, of course, the section below the feed, okay? The feed plate. Feed plate being included. So if you use N for the general representation of the stages in the enriching section, in here we will represent the stages here as M because we cannot keep on using N because we use it already on the top section. So in here you have the reboiler, you have the bottom's liquid. This is the mole fraction of the vapor that is introduced back into the column to flow counter current to the liquid that goes down. Now, in here, you could see that the stripping section operating line was already drawn. The enriching section operating line was not drawn. That way, you will understand that you will be able rather to focus on the stripping section operating line only. So just like the way we've started with enriching section operating line, you need the mole fraction of the bottom's liquid to start with. So that's your X sub W. This mole fraction, together with the mole fraction in the distillate, is given most of the time in the problem, both that of the distillate and the bottom's liquid. You project it up and also make it rest on the 45-degree line. Now, in the stripping section operating line class, we have the slope as Lm over V sub m plus 1. Also, not given or specified in the problem. But we don't do, take note, we don't do the stripping section operating line the way we do the enriching section operating line. What do I mean by that? We only need one information for the stripping section operating line, because this point that you have here projected on the 45-degree line will be connected to the point of intersection. To the point of intersection of what? To the point of intersection of your, let me do this first, of your enriching section operating line and the feed line, which I'm going to discuss next. This one will have an intersection to a third line that will be drawn on this same equilibrium diagram. Wherever is that intersection, you connect the point of intersection to the X sub W here of your stripping section. Then you will produce this line. So again, I'd like to emphasize that the stripping section operating line will only have one needed info, and that is the X sub W. Just like your enriching section operating line, it has also its material balance. So in here, you have V sub m plus 1 is equal to L sub m minus W. So your V sub m plus 1 is this particular vapor phase leaving stage M. This one, stage M. And you have this one as Lm. This is your Lm, the liquid phase. And this one is your bottom's liquid. So if you notice in this section, you have this as one leaving phase, you have this as one leaving phase, and you have one entering phase, the L sub M only. So when we do our material balance only in this section, it should be Lm equated to the sum of V sub m plus 1 and W, because of the fact that these two are phases that leaves this section, whereas Lm enters this particular section here. Now, our component balance for the stripping section, just like the way we do it with our enriching section, has the same pattern with it. You just multiply the one that you have here in the total material balance by the corresponding mole fractions of the phases. Okay? Y for the vapor and X for the liquid phases. If you divide also by V sub m plus 1 this equation, you will come up with the stripping section operating line equation. But as I have emphasized a while ago, we don't need the slope of the operating line of the stripping section. We don't need also the y-intercept of the operating line of this section, because we will just connect the X sub W of your stripping section operating line to the intersection of the enriching section operating line and the feed line. Okay? Now, we need that intersection. We need the intersection of the enriching section operating line and the feed line. But before we know that, of course, there's a need for us to know what information is needed to plot or know the feed condition. To know the feed condition and to properly reflect that in our calculations, even if we don't do graphical approach, there's a need for you to understand what is this Q, because it appears in the equation of your feed line or the Q line. So McCabe defines it differently. Gianco please defines it differently. So if you get a problem from McCabe, it will ask a totally different question in relation to feed condition. If you get a problem from Gianco please, it will also ask a different style of question. It will have a different style of questioning regarding the feed condition. So it's really important why I'm emphasizing this. It's very important that you don't read only McCabe, but you also read Gianco please, because we don't know what kind of problem will any assessment that is given you, whether here in the undergraduate studies or in your licensure exam, how hybrid it could be. It could be a hybrid both of Gianco please and McCabe. But nonetheless, I have the two definitions of the two authors here. According to Gianco please, Q is the heat to vaporize 1 mole of feed at its given entering conditions per molar latent heat of vaporization of the feed. This is the way it is defined there. And in the manner of questioning, it's also like this. So in his sample problem, the manner of questioning is also based on this particular definition. Something to do with the heat to vaporize 1 mole of feed at entering condition divided by the molar latent heat of vaporization of that same feed. McCabe defines it differently. So McCabe defines it as the number of moles of saturated liquid produced in the feed plate by each mole of feed added to the tower. So how much saturated liquid is going down your feed plate for every mole of feed that is introduced into your tower. Every mole of feed that is being introduced into your tower. This is the definition of McCabe on the Q. This Q will not be difficult if your feed has this particular defined states. What do I mean with defined states? If the problem tells you that the feed is saturated vapor, the value of the Q is automatically 0. So you need not worry which of these two definition will you use, that way you'll come up with a very important Q value. If the feed is saturated liquid, automatically Q is equal to 1. If the feed is cold liquid feed, this is the time that you need to specifically determine the value of the Q, because Q is any value greater than 1. So if the feed is cold feed, make sure that the Q value that you have computed will be greater than 1. If it's other than this, if it's less than 1, then probably there's some error in the manner you determine your Q. Now, how do we determine this, Miss Ali? Of course, there's a formula used in determining this one. Okay, for cold feed. For superheated vapor, the Q is less than 0. Now, if the feed is part liquid and part vapor, Q is the fraction of the feed that is liquid. This is very important. I like to emphasize this one. This is nowhere specified in any of the definitions, but in the sample problems that you will encounter, especially in Gianco please, if the feed is a mixture of liquid and vapor, that percentage of the feed that is liquid, that is the value of the Q. For example, your feed is 40% liquid, 60% vapor. The Q value is automatically 0.4. If it's 30% liquid, 70% vapor, the Q value is automatically 0.3. So that portion of your feed which is liquid is the Q value. So if it's a mixture of liquid and vapor, the Q value is between 0 and 1. So Q is greater than 0 but less than 1. So the primary challenge class is when your feed is cold and when your feed is superheated. So you can check it in here based on this particular condition whether the Q value that you have determined is correct or not. However, the thing is sometimes or most of the time the problem does not even mention that your feed is cold or your feed is superheated. You will just be left with the two definition here, whichever is appropriate to use depending on the data that is provided by the problem to tell you or to give you the Q. Because whether we're solving the number of stages of your distilling column, that will tell us how high is your column in terms of design, and analytically or graphically, most of my students that has taken this subject, the main culprit always while the students have everything gone wrong is the Q. Meaning, all their computations will be wrong if this Q value is wrong. So you have to make sure that the Q value that you have calculated or determined is correct, whether the procedure is graphical or analytical. So this has to be correct because the material balance part in distillation wherein you use the overall material balance equation and the component balance equation is just 2% or probably 5% of the entire thing that is related to the problem of distillation that you are required to solve. So it's very important that you know this Q. Okay, now in relation to this definition of the Q based on the heat vaporized per mole of liquid entering the column divided by the molar latitude heat of vaporization of that feed, this is the formula that you will use as provided by Gian because that is his definition. So the Q is equal to the ratio of these two differences. The difference of the enthalpy of the feed at the dew point minus the enthalpy of the feed at the entrance condition. H sub V minus H sub F, whereas in the denominator, you have the difference between H sub V and H sub L, where H sub L is the enthalpy of the feed at the boiling point. This is the saturated vapor enthalpy on the feed condition. This is the saturated liquid enthalpy at the feed condition, whereas this is the enthalpy of the feed. These enthalpies are determined using the equations that were provided for you in your thermodynamics in relation to Cp delta T. Okay, there will be a sample problem that we will use regarding the use of this particular formula. Now, in here, I have placed the equation, this bigger. You will be able to read this in McCabe. So by the way, I'd like to emphasize that you should have both soft copy of McCabe and John Cooper's. That way you can read both of them in all the topics here in separation processes. If the feed is cold liquid or superheated vapor, I refer you to these equations in McCabe. So these two equations allow you to solve for the Q for cold liquid and superheated vapor feed. Okay? If your feed is cold liquid or superheated vapor, these are the equations that you are to refer to. This is on the 7th edition of McCabe. So make sure that you check on this particular equation. Now this one are just the equations regarding the relationship of the amounts of the liquid that is this one for the stripping section that is entering your stripping section, the amount of liquid that is leaving the enriching section, if you can still remember, I've shown to you this a while ago, and this is the vapor that enters your enriching section, okay, in relation to Q and the amount of P. We very seldom use these equations because we use this equation for Q and the equations that are provided by McCabe. We don't use these two like solving it simultaneously with Q as the unknowns, or the others are known with even the Q and we need to find the other values of the streams in here. This is just for your information. Okay, so we use this one. Yeah, I'd like to emphasize the use of this and the equations in McCabe. So check in McCabe as to the equations that will be used by you in determining the Q. So now that you know the Q, based on these two definitions, this is the equation of the Q line. This is the slope of the Q line, and this is its y-intercept. Your Q line being called the feed line, so otherwise known as the feed line, when plotted will need the XF. This one, the XF. What is this XF? This is the mole fraction of the more volatile component in the feed. So in the case of the benzene toluene system, this is the mole fraction of benzene in the feed. So the XF. When you plot your feed line, you either use the slope or you also use the y-intercept. So you see how important is the Q? It appears in both the slope or the y-intercept of your feed line equation. So just like the enriching section operating line, you have the choice whether you use M here or B. As long as you properly plot it, it doesn't have any problem with me. Anyway, later on, when you use the analytical approach, you'll still be using analytically this equation which you have set up for the feed line. Now, before we end this one, I'd like to show you where the feed line is. Here. I think it's in here. Make it smaller. So, you could see in here, these are your, this is not the way you draw it. You only have 3 operating lines in your equilibrium diagram. So, the enriching section operating line, this one, the stripping section operating line, and the feed line. So if your feed is saturated liquid, this is your feed line, Q equal to 1. If it's saturated vapor, this is Q equal to 0. Okay? If it's superheated liquid, it's this one, greater than 1. If it's a mixture of liquid and gas, it would be something like this. So this is the orientation of your Q. Your Q, if you notice here, I will now have it enlarged. Will be plotted starting with the XF value. The mole fraction of the more volatile component in the feed will be projected on the 45-degree line, and that's the starting point of your feed line or your Q line. And using the y-intercept or the slope of the feed line based on the equation that I have shown to you a while ago, this one or this, you plot your feed line. So for example, this is, you have a saturated feed, so there's no need for you to determine the Q. Because automatically your feed line will be vertical and we're starting with XF. The intersection of your enriching section operating line, the intersection of your enriching section operating line and this feed line would be this, right? If your feed is saturated liquid, what happens is you just connect the X sub W point here of your stripping section operating line to this point. And that's where And that's where the intersection of all three operating lines should be. So you have now 1, 2, 3. And this particular orientation of your operating lines will be the one to determine how many stages should be in the enriching section, how many stages will be in the stripping section, and how tall will your column would be. So the number of stages allows you to determine the depth, should I say, how tall your column should be. Okay, so in terms of column design already. So it's also anchored upon the desired purity of your distillate. So your problem will specify the desired purity of your distillate. So this is the graphical approach of determining the number of stages in your column connected to the length of the column. So it's also in section 13-19 of your handbook. Now, I'd like to end here on the concept of the location of the feed plate. By the way, class, when you do write or draw the three operating lines to determine the feed plate location, it's the feed line that determines that. I will show to you in here. Before that, I will erase the markings that I have. So the feed plate location, it will be best discussed in here. Okay? Now, you have here a condition, a sample condition, and you have already drawn the three operating lines. Enriching section, and you have the stripping section, and you have the feed line. When you determine the number of stages graphically, you draw this stepwise process until you reach or go beyond the X sub W point in here. The feed plate location, class, is that this one is not the proper way of doing it, by the way. Why? Because when you have drawn here the stepwise process or the stair-like line, you don't finish it until the part wherein you have already ended the way you have drawn your enriching section operating line. At the very first opportunity where the intersection of the three operating lines met that you can transfer to the next section, you do that. So meaning the proper way of doing this would have been, you have stage 1 here, then you have stage 2 in here, and then you transfer here right away. Not that you're going to finish everything in this section based on the length of the line that you have drawn. So it should have been transferred here, then you draw another one, you have here. You continue drawing until you go beyond the X sub W, or you rest right away in here. But in this case, you don't rest in here because you haven't touched the equilibrium curve. You extend it, that way you touch the equilibrium curve. This is not the correct way of doing it. The correct way of doing it is like this. So at the very first opportunity wherein you can transfer from one section to another, after you have passed through the point of intersection, you do that. So even if this line is extended, you transfer in here on the next section. So where the transfer occurred, like from one section to another, is the location of the feed plate. The problem oftentimes asks where the feed plate is, or what is its location if we're going to start on the top part of the column. So the feed plate location in this case is the second plate. Now, the number of stepwise or stair-like lines that you have here, the number of steps that you have drawn, determines the number of stages. However, we subtract 1 because the last part in here is the reboiler. It's not part of your column. So we just answer 3. And I like to erase what I have written because in here we don't say it's 3 or 4. We don't say number of stages is equal to 4. Why? Because you did not rest here right on the X sub W. In terms of the area of the entire step here, you only cover this area. So as to what is the percentage of this area in relation to the entire step, that would be the corresponding number of stages here, including the reboiler. So I would say this is more or less 3.5. Probably if I divide by 3. Sige. So this would be around 3.70. It's not equal to 4. But I need to subtract 1 because as I've said, the last part is the reboiler. So your column in this case only has 2.7 stages. Okay? There are instances wherein you don't subtract only 1. We subtract 2. That will be discussed tomorrow. Okay? Because it's already 6:30. You will understand this better tomorrow if when I discuss a sample problem in relation to what we have discussed tonight. You have beside you a, shall I say, an X and Y diagram or an equilibrium diagram for benzene and toluene. Okay, ha? I'll erase first what I have written here. Okay, and stop sharing. That way we can discuss if you have any questions.